بسم الله الرحمن الرحيم. السلام عليكم. في البداية في معلومات مهمة جدا، تغييرات حصلت على الكورس بالنسبة للجريدينج. So please focus with me so that you will understand how things will be from now on. The final exam, FOA exam, is cancelled. There was 30 degrees dedicated for that exam. It will be, this 30 degrees will be divided as 15% for final project. Final project is different from the other project which we are supposed to present shortly. Final project will be based on lab simulation. Lakshmi will prepare a video for you how to do the simulation for the lab, and you will be given after mastering the basic. It's very simple. There will be video explaining all of this. You will be given a problem for transmission line or for whatever, and you will submit your solution for that problem. 15% from this final exam will be divided as per the following. No, let me explain it. The final exam, which was having 30%, 30 degrees, there will be no final exam. This 30% will be divided as per the following. 15 marks will be on a final project. Final project is based on lab simulation. Lakshmi will provide video illustrating how to do the simulation on the lab, and you will be given a problem to solve it. This has 15 degrees. Now the other 15 degrees will be divided as 5 of them will be added to the assignment. 5% will be added to the reports, and 5% will be added to test number 1. Test number 1 will be 20 marks instead of 15 marks. So the day after tomorrow you have makeup exam. Remember, this now is 20 marks. So work hard on that. While you are doing the makeup exam, remember that we are in our way to close chapter 6, and the second exam will be there, but there will be also this as per the new plan. There will be no second exam. It will be between 2 to 4 quizzes. Between 2 to 4 quizzes, simple quizzes. For the project which already you given the information and you selected your project, this is as before 15%. For this one you will make PowerPoint presentation so that you will present it using the PowerPoint. For the labs, as per earlier schedule, there was 5 labs. You already completed 3 of them, remaining 4 and 5. 4 and 5 will replace them by something to give you the foundation for the simulation. So after you have understood the simulation, lab simulation, maybe you will be giving a quiz about that. So this will replace lab number 4 and lab number 5. For the question of don't worry. We'll do extra quizzes I want you to get the maximum grade that you can, whether in labs, whether in quizzes, assignments, whatever. Maybe I will replace the quizzes by assignments. Just be serious. We know that the present circumstances are tight, but from your side, try to be showing the maximum that you can. Then don't worry. Is this clear now before I move to other? By the way, tomorrow we'll have a meeting, all the teachers for this course. We will decide exactly how will we do the final project, but it will be something like that, simulation on the lab. Any question before I switch to the other subject? Work hard on the project. The project has 15 marks. In the present circumstances, these things the people who are asking for to modify their grades. It's an opportunity. But I don't know, so far only I received from one group of you the project. If you are going to present at the end and there are so many mistakes or so many gaps, you cannot do anything at that time. So take this into consideration. Any other question before I start the new subject? Any more question? Now we'll continue the last subject of this chapter, which is about the capacitance. Now, for your information, this chapter about transmission line parameters, chapter 6, which has almost around 100 pages in your text, is very simple. You will see after we complete the chapter, I will be providing you with only maybe 1 page will summarize all the information that you need in this chapter. This chapter has built on finding the parameter of a transmission line: resistance, inductance, and capacitance. These variables of the transmission line are controlled by two things. One thing is the chemical structure of the material. When it comes to resistance, we are talking about resistivity. It's about how much are there free electrons in the material to have good conductivity. Conductivity is the reciprocal of resistivity. When it comes to the inductance also, it's related to the magnetic field built around the conductor. Capacitance, which we discuss, it's about the electric field and how much the conductors can have electric field strength between them. So this is dependent on the material. When we say conductivity for resistance, permeability for the inductance, and we'll come here, permittivity to capacitance, all of these are related to the chemical structure of the material. It's different from material to another. And from the language perspective, they are the same. When we say conductivity, permeability, permittivity, يعني موصلية, نفاذية, سماحية. From the language perspective, it's the same. It's talking about the chemical structure of the material. So it's different from material to another. This is simple because these parameters are readily available and you can get them. The other factor is the dimensions of the transmission line. Conductor dimension, radius, length, spacing between conductors, bundles of conductors, single circuit, double circuit. So everything in this chapter, all of it, it's regarding mathematical calculation of these distances between the conductors and based on the structure of the transmission line. Only mathematical. So the information on this big chapter are very simple. We will see after we finish, I will give you examples and also examples which are coming in the final exams. And I will summarize this chapter completely by one page, which is enough to have any information you needed to solve any problem. The only thing is to understand the physics, what we are talking about, only a general understanding, so that when you see the geometry of transmission line with the conductors, how will you evaluate mathematically these distances or spacings or radius, whatever. This has nothing to do with the physics. The physics is only simple. We said conductivity, permeability, and permittivity. There you have rho for resistivity, then you have mu for permeability, and now you'll see here epsilon for permittivity. These are simple given information from the physical point of view. All other things, what you saw, single line, two line, three phase, bundled, not bundled, double circuit, all of them, as you will see, is mathematical calculation. If you understand the lecture, it will be easy for you because it will give you a need how to solve these problems. The other physical information you need are simple and available in the formula sheet for you. Already we finished the resistivity and inductance of transmission line. Now we'll talk about the capacitance. Capacitance, by definition, is when you have two plates, they have equal but opposite charges and there is voltage drop across them. This is the concept of the capacitance. Two plates, they have dielectric in between. It might be air, Teflon, glass, rubber, plastic, whatever, this dielectric, which is insulating material. And they have charges on these opposite plates, equal charges but opposite in sign. So normally these charges are equal but they have opposite sign with a voltage drop between them. This charge, which is inside these two plates, this medium, is by definition equal the capacitance of this material multiplied by the voltage. What is capacitance? That's what we are going to find for the transmission line. So based on this, capacitance will be equal the charge divided by the voltage drop between the conductors. And this is what we are seeking, like we did with the inductance. That's what we will be doing with the capacitance. We'll find the charge, divide the charge by the voltage, and this is the capacitance of the transmission line. If you recall from physics, when you have two plates and electrons passing through them, there will be electric field this electric field is basically, when the charges are moving there, is the voltage divided by unit length. How far the electrons, current is flow of electrons, will travel there. Per unit length, there will be different field intensity. So we have to understand what is meant by electric field intensity, which is E. It's simply the voltage gradient per unit length inside this medium or dielectric. If I provide this electric field, it might be simple as a battery. I connect the battery to two plates. You saw this before in physics. Connecting battery with plus minus to different plates, this will get capacitance. This electric field will be different if between these two plates I have air, rubber, glass, mica, Teflon, whatever insulating material, it will be different. My electric field is constant, but the flux intensity of this electric field will be different based on the material. This material will decide how much, like the permeability of the material for the inductance. Different materials will give different permeabilities. The same thing. Here, I told you, whether we say conductivity, permeability, or here, permittivity, samahiyya, from language perspective, they are all the same. So the permittivity from permission, how this medium will permit the electric field to pass through it. So by this I have another term which is D, electric flux density. This electric flux density is divided as epsilon multiplied by E. So you have E is constant, your electric field, but this medium has got epsilon, similar to mu in more magnetic field, magnetic system, and to rho for resistance. This medium has this constant, with this constant epsilon, product of two parameters, mu r and mu naught. Mu r is the relative permittivity. Mu naught is the permittivity of the free space, exactly similar to the permeability in the magnetic field. Mu naught is given the value of 8.85 times 10 to the power minus 12. This is mu naught. So these concepts, this physical concept has to be understood when we are talking about capacitance. Capacitance is being provided if I have two plates with voltage drop across them. There will be accumulated charge on each plate, and there will be electric field. This electric field will be the strength of this electric field, which will be presented as flux, electric flux density, will be decided by this medium. How much is the permittivity? How much permission this medium will give to the electric field? For our transmission line, there are different voltage traveling through the transmission line, because also the different phases, there will be voltage drop between the lines, between the line and the earth, and this will make charge accumulated on the conductors. The dielectric here is air. They are suspended in the air. So the dielectric material is the air. And there is electric charge, because current basically is based on charges, movement of charge, rate of charge per time this is the current. So this different voltages will create charges accumulated on the conductors of the transmission line, and there will be capacitance, because you will be having two different charges in two lines, whether phase to phase or phase to neutral, and your dielectric is between them. This charge is available even if the line is open circuited. So normally when we do maintenance for a transmission line, before doing any switching or connection or termination, we'll discharge it, as you can see here in the picture. They will discharge the line even if it's open circuit. There's a charge stored in this transmission line. So this is very important. Something dangerous is available on the transmission line even if it's open circuited. Now if you look at the transmission line, conductor of the transmission line, you have the conductor and there is electric field intensity and electric field density moving radially from the center of the conductor outwards. We'll see in the next picture how it will be. It's from the center radial to the surface. If you have this magnetic flux density, which is D, passing through unit area dA, there is one equation known as Gauss law. If I do this integration, closed surface integration upon the entire surface of this conductor, I can take part of it as we did before. If the conductor is with radius R, I will take radius X, for example, I integrate it. I will get the total flux density passing this surface. The surface, this is the equation, this is the surface through the closed surface. If I integrate this, I will get the total enclosed charge inside this conductor. This is Gauss law. Now, this is the conductor. This conductor has the charge radiated radially from the center of the conductor to the surface. So I have the cross section, which has a radius, and the transit line has a length, which is L. This is the radius which I will select. I will select X. Same philosophy that we did with the derivation of the inductance we are doing here. We are taking X outside this conductor. We want to see how much is the capacitance there. So if I integrate from based on the last equation, I'm integrating D with relative to the unit area. So if I get this area, by the way, the area is like, if you have cylinder, if you have paper, fold it like cylinder, the surface area will be the 2 by R multiplied by the length. This is the area of when you open this cylinder, 2 by R multiplied by the length. And this area, after integration, multiplied by flux density, electric flux density, you will get the total enclosed charge in this conductor. Or this area is 2 by X multiplied by L. Exactly as if you have paper folded like cylinder, it will be like at the end, like you have a rectangle. 2 by X is the perimeter of the circle multiplied by the length. So D multiplied by A, which is 2 by XL now, is equal to the Q, the charge per unit length, multiplied by the length. Q is the total charge, small q is the charge per meter. The same philosophy that we did for resistance or inductance. We are going to calculate it per meter. So it's simply like that. Because we defined the capacitor at the beginning, now we want to find an expression. First, we have to see how much charge we have there. This charge, enclosed charge, by Gauss law, I just integrate the electric field density with the area. If you cancel L here with L here, you are getting D equal Q over 2 by X. This is D. For E, remember that we said that D equal epsilon multiplied by E. So E, it will be equal this D over epsilon. E, the electric field intensity. Electric field intensity is the electric field strength equal the charge divided by 2 by epsilon X. If you have the conductor and similar way of the inductance, we are going to find the capacitance between 2 points, P1 and P2. P1 and P2 are external to the conductors. They are at distances or radius D1 and D2 respectively from the center of the conductor. Here, the integration is dot. If you remember from mathematics, when you have dot, it will have a value when the two vectors are in the same direction, parallel to each other. So here, if I want to integrate from point P1 to P2, if I move radial from the center of the conductor to the point P int, then I'll move to P2. One of the paths is parallel and the other is perpendicular. The perpendicular normal one is 0 because this integration with dot means that it will be having value only if they are in the same direction. Don't bother of that. This will result as if you're integrating from D1 to D2, regardless of the path. As if you're integrating from D1 to D2 because you are catching one of them only. So if I integrate, we said E is basically the voltage per unit length. So if I want the voltage, I will multiply this E by DL with the distance from B1 to P2. If you integrate this, you substitute for B2 by D2 and D1, and you are integrating E dx. You can see here the relation between the voltage and the electric field. So this integration E dx is simply will be transfers to ln as we did for the inductors. Everything is constant. We are integrating in respect to x. So q over 2 by epsilon will be outside the integral as constant. Then I will integrate 1 over x. 1 over x, if I integrate it, I will get ln d2 over d1. Ln d2 minus ln d1 equal ln d2 minus d1. We are concerned about this last term. This is the voltage between two conductors. Now, as we started before, we'll start with single phase two-wire transmission line. Now, one important information, the difference between single phase and three phase, because this was done for the inductance as well. And we have almost the same expression with only different factor. Sometimes here 2 or here 4. Why is this difference between single phase and a three phase? In a three phase system, when normally, suppose I am laying a cable to feed one factory. I want to the voltage drop for this cable. This cable was like this one, three phase. For my calculation, I will take the length of the cable. For the resistance or whatever inductance, I will take the length of the cable. Why? Because each phase is having a current, but the neutral one, if it's balanced system, which is assumed to be balanced system, will be zero. So I have only one conductor from the source, from the sending end to the receiving end in three phase. It will be one conductor feeding that factory. But if I am laying a cable, single phase cable, there will be a return back. Instead, for example, suppose that the length was 500 meter in the three phase. I use 500 meter in the three phase. Now, if I use single phase cable, the length, total length will be 1000. I have return path. For single phase, you have the complete, this you can apply to any single phase circuit. The length of the path of the current will be hen and forth, return conductor. So the length will be as if you are multiplying the length by 2. This is the only difference between single, and we will see it. We saw it in the inductance, now we will see it in the capacitance. So if I will start with single phase two-wire transmission line. One of them has the charge Q plus, and the other is minus Q. Same charge, same magnitude, but different opposite sign. One of them is A and the other is B, and distance D between them. Each one has a radius R. This is single phase two-wire transmission line. Again, I told you this chapter will be summarized by one page. That was all you need. But here, the only thing that to have a window to understand difference between when you see in the problem single phase. At the end, you will see the fact only this one of them will be multiplied by 2. Reason is that, as I explained, for three phase we have one conductor per phase. This is the length we are considering. The neutral is having 0 current. But for single phase like this case, I have return path. Now we said that we have already evaluated the voltage as a Q, small q, which is the charge per unit length, over 2 by epsilon ln D. Now I see here, this is VAV, the voltage between A and B relative to A. This is the voltage from A to B provided by the conductor A. So it will be D over the radius of the conductor, which is R. Equation that we derived just now, which is D2 over D1. Now D1 for you is the conductor itself. It's R. D2 is D. So from that equation that we got, we'll replace D2 by D and the D1 by R. So this is VAB. Always remember that VAB means VA minus V. Voltage drop between A and B. VA minus VB. This is produced by A, and the other one, now the voltage at B will be VBA, and the charge will be QB now. Look at the second equation now. you have VBA. Always in electricity, VBA is minus VAB. If you change this reference point, you will change the sign. I can replace VBA by VAB, the second equation. I just switch the voltage from VBA to VAB, and I will provide the sign because this is minus now. It's the same equation, the same second equation. The only thing that I replaced VBA by VAB. So I change the sign. VAB by definition equal VAB at A minus VAB at B, which will lead to QA over 2 by epsilon ln D over R minus QB over 2 by epsilon ln D over R. Same equation before, just substituted. QA and QB, they are the same magnitude, but QB is a negative sign, so minus will be positive. I have now replaced QA by Q, QB by Q. Since it's minus, it will be Q over by epsilon multiplied by ln D over R. Only mathematical simplification. Now the capacitance, remember as I told you, always go to the last station. At the last station we put it at the beginning. We said that the definition of the capacitance is Q over V. So I found an expression for V. I divided Q by V. If you divide Q over the V, VAB, you will get this Q over by epsilon D over R. Q will be cancelled with the Q. Then you will be getting the capacitance as by epsilon over ln D over R. This is the only important equation that we need. This is the definition of the capacitance between the two lines. Capacitance between two lines. Remember, we took two lines, A, B. Suppose that we want to find the capacitance between one of the lines to the neutral. Neutral point will be a point which is midway between the two conductors. If you select a point, there will be the neutral or the ground placed, this midpoint will have 0 volt. So if I select this point here, then the capacitance to neutral will be like this. So as you can see here, now the capacitance to neutral is twice the capacitance between the two conductors. Remember, this is capacitance. It's opposite to resistance. For if they are resistances, you will add them. But for capacitance, it's the opposite. 1 over CA plus 1 over CB, or you just multiply them like you do the capacitors in series is like resistors in parallel. So here, Cn, it will be 2CAB, because the equivalent capacitance for them as if they are resistance in parallel. So you will get CAB. So normally the capacitance to neutral is double the capacitance between the lines. Why? Because this neutral point is point midway between the two conductors. So if I want to replace the capacitance between the lines to two capacitors, these two, equivalent of them will be this CAB. This cannot be unless each one of them, CAN or CBN, will be twice the capacitance, so that if I take the equivalent of them, I will be getting half of that. That's why the capacitance to neutral is always twice the capacitance line to line. So for the capacitance Cn, you can name it CAN or CBN. The same expression above, the pink one, you just multiply by 2. So far, before I continue, is there any question, anything, any point is not clear? Now, based on this same philosophy, as we analyze the inductance, we'll analyze the capacitance now. See here, from this expression of the capacitance, it will be opposite to the inductor, because the ln D over R now is down. So things will be opposite. So based on this, as I told you, this is important to understand it. When we have a transmission line at different voltages, whenever we go higher with the voltage, we have to make the spacing more, so that will be proper insulation. So the distance between the conductors in the 400 kilovolt, for example, is much more than that distance for the 11 kilovolt. Based on this, this physically has to be understood. I'm talking about the capacitance. I'm talking the capacitance, which is the field enclosed between the two conductors, like two plates. Whenever they get closer, the capacitance has to increase. So for this, based on this, the capacitance of the 11 kilovolt in this picture is much more than for the 400 kilovolt. This can be understood from the equation, also from the physics. Whenever you have two plates to make capacitor between them, increase the spacing, you are reducing the capacitance. Decrease the spacing, the plates are coming close to each other, the capacitance will increase. This can be also shown for the buried cables. When you say buried cables, it means that the distance is even very, very close. Sometimes the cables in the underground cable almost touching. So the distance is very small now. So the capacitance is very high. That's why when we do testing or termination for the underground cable, it's crucial to discharge them even if the circuit is open. The capacitance is very high in buried cables. A new simple thing based on that is the admittance. The only thing that if we get the capacitance, you remember that if you multiply by the angular frequency omega, you will be getting, before we talk about the inductance, now for the capacitance. For the capacitance, it's opposite, because if I got this, I multiply the impedance of the capacitor is 1 over omega c. So that's why I call it now admittance, because the reciprocal of that will be the impedance of the transmission line. So this admittance is the multiplication only of the capacitance with the angular frequency. With this C small is per unit length. Suppose that the length of the transmission line is D, I can get the entire capacitance of the transmission line. Impedance is 1 over the admittance. Simple thing, information in this page is mainly how to get the impedance. Impedance is the reciprocal of the admittance. Admittance is omega multiplied by the capacitance, because you know from circuits the impedance of the capacitance or the capacitor is 1 over omega c. Now we'll see this example. This example, you remember last time I stopped at the example. This was the same example, but I added to it the capacitance. For this example, we'll be seeing everything here. How to calculate the resistance, inductance, shunt capacitance, total series impedance, total shunt admittance. This is single phase transmission line. Remember that still we are at the single phase. For 3 phase will be different in the formula. So this I can put it in this way. These are the 2 transmission lines. Each one has a radius of 2 centimeters. And I've given the temperature 20 degrees. The required is the series resistance, series inductance, total impedance, series impedance transmission line, and the admittance of the transmission line with the shunt capacitors. Transmission line is 30 kilometers long. Always try to understand the question and to translate this text of the question to like this sketch or something that you know that you will be using. And for example, this temperature is given for a reason. Let's first start with the resistance. Resistance, as we saw before, it's rho multiplied by L over A. I have the radius of the conductor. This is hard drawn aluminium conductor. It's aluminium. I have to take the rho, the resistivity of aluminium. We explained the resistivity. We saw that resistivity is best for silver, then copper, then aluminium. We've selected aluminium because it's cheaper and lighter. But In this case, if we are going to use aluminium, we'll be using bigger radius. So I have to substitute for the rho of aluminium in this equation. Rho for aluminium is 2.83 times 10 to the minus 8 at 20 degrees. Remember that there is an equation, if you remember the temperature constant, there's a relation between the resistivity and the temperature. The higher temperature, the higher resistivity. So normally resistivity is given at temperature, that's why the temperature 20 is given. And if I ignore the skin effect, we said that for 50 or 60 hertz, the skin effect is not severe. If I were to take the skin effect will increase the resistance. Resistivity will increase. Always the AC resistance is more than the DC resistance. But since I'm ignoring the skin effect, I have the rho 2.83 times 10 to minus 8 ohm meter. So I only substitute for this, and I will get, you remember that also when we say R, we are talking about the total resistance. Small r is resistance per unit length. So now I will find a small r, which is per unit length. Just I have rho over A. I multiplied by 1000 here to get it per kilometer. The multiplication with 1000 here to get it, because normally if I don't put 1000, it will be by meter. So I've given that length of the transmission line by kilometer. Here I can just rho over A. It will be 0.0225 ohm per kilometer. This is the series resistance of the transmission line. Now we want the series inductance per also kilometer of transmission line. You remember this? This is exactly the same before. Either you will use this equation, or if you remember, we simplify it. We come to this 1 over 4, we put it as ln e to the 4, and it was at the end mu over by ln d over r dash, where r dash equal r multiplied by e to the minus 1 over 4. Either of them is the same. We said at that time it's only simplification. So this is the equation for the single phase transmission line. I substitute by d, I have d, they are 1.2 meter apart, and I have r 2 centimeter. I convert it to meter, multiplying by 1000 to get it per kilometer. This is simply the calculation of the inductance of the transmission line. Now the shunt capacitance, also I want it per kilometer. If I'm going to find CAB between these two conductors A and B, I will be using this. We just derive this by epsilon over ln d over r. Epsilon will be given and known, 8.854 times 10 to the minus 12. B is the same, 1.2, and R is 0.02. Again, by 1000 to have it farad per kilometer. This is CAB. This is the capacitance between the two conductors. If I'm looking for the series impedance for transmission line, impedance, I have R, I have L. Multiplying L by omega, which is 2 by F, I will be getting X or XL, and I have calculated the value of both of them. I can put it like this, R plus JX. R is already calculated from the first step. Z now is only the L that I got multiplied by omega, 2 by F. Total, when you say the total series, remember that always when you say L and R small, this is per meter. They are always given as per meter in the, even the manufacturer data sheet. If the total, I have the total length of the transmission line, which is 30 kilometer, I multiplied by 30 kilometer, what will be given now in ohm. This is the series impedance of a transmission line. Shunt admittance, which is YC. We say admittance for the capacitor because capacitor impedance is 1 over omega C, 1 over YC, 1 over the admittance. So the admittance is omega multiplied by the C. If you do this, you will be getting the shunt admittance. Normally the unit is Siemens per meter. Total shunt, we are having 30 kilometers. We multiply by 30 kilometers. This is Y, 1 over Y will be the impedance, and this is the total impedance of the transmission line, total shunt impedance. Is there anything not clear in this example? Any point is not clear in this example? Now we'll come to the three conductor case. You will see the difference, very small difference. This is the most important thing. When we come to the three conductors, three-phase circuit, double circuit, bundle conductors, as you will see in the examples, we saw some examples, but I'll be giving you examples which will cover so many different cases. It's only mathematical. I said at the beginning, for resistance, inductance, and capacitance, any of them, they are decided by two things. One is the chemical construction of the material, which is represented by resistivity or the conductivity in the resistance part, permeability in the magnetic field, and permittivity in the electric field. This is given as rho, mu, or epsilon. This is simple. The other factor is the dimensions. The diameter of the conductor, equivalent diameter. Sometimes the diameter will not be easy to find. It will be finding the equivalent diameter or geometrical mean diameter. Also, the distance. Distance, sometimes you have different arrangement of the circuits. That will be also mathematical finding of the geometrical mean distance between them. So we have, suppose that we have these three conductors. They are equilateral triangle. Distance between them is d, and we'll consider that QA plus QB plus QC equals 0. The same as the equation before, IA plus IB plus IC equals 0, but now we are talking about the capacitance. It's the same, because the current is normally the rate of change of charge. Based on the same equation that we got, we want to find VA. VA, the voltage at A, at phase A. This is very similar to the procedure that we took in finding the inductance. Will be self voltage generated from this phase A. So I'm dealing with 1 over R, the radius of the conductor, and its charge, which is QA, plus there is, let's say, a mutual interaction from phase B and phase C. When it comes to B, it's the QB. We have the same common factor, 2 by epsilon, 1 over 2 by epsilon outside. So I have QB here, ln 1 over D. It's the same equation before, but now I am applying this as superposition for phase A from a three perspective. One of them is from the conductor itself, I will be using R, and from the two others, I will be using the distance, D. One of them is QB, one is QC. Again, with the same philosophy, if I take 1 over D as common, I will have a QB plus QC. A QB plus QC from the equation is minus QA, same as we did with the current. So QB plus QC is minus QA. So I will be having the equation, same common factor, 1 over 2 by epsilon, a QA ln 1 over R, IA minus QA, I replace the QB and the QC by QA, multiplied by ln 1 over D. If you do this simple mathematical procedure, you will be getting VA equal QA over 2 by epsilon ln D over R. As you can see here, things are similar. Things are very similar. This is VA. Again, all my procedure is to find C. C is a Q over V. So I divide QA by VA, which I got. I will be getting 2 by epsilon over ln D over R. The same procedure with the inductance. There was only one of them single phase and the three phase double the other. We explain why we are getting double. But for the capacitance, it's opposite now. So the difference between this and the previous one single phase, you remember that one was pi epsilon over ln d over r. Now we have 2 pi epsilon. But this is the opposite to the inductance. Now, sometimes, but this is only just for information. It's there in your textbook. You will not be using that. But to understand that sometimes this charge is, because we know that the charge is the multiplication of the product of the capacitance with the voltage. Sometimes it's being summed as self-one and mutual capacitances. So they will put them in a matrix. For example, here, if I want to find, for example, a Q1, by this arrangement of the matrix, it will be C11 times V1 plus C12 V2 plus C13 V3 plus till I reach C1n by Vn. This will be Q1. Other charge will be like this. This is, I don't think that you will need this, but to show you that sometimes because when we talk about inductance or capacitance, there is, as you saw, mutual things. Charge affect each other, magnetic field affect each other. That's why for inductance and capacitance we are looking for these equations. For resistance we don't need that. There is no interaction for resistance of conductor A to the conductor B. So that one is simple. But when it comes to inductance, magnetic field, and capacitance, electric field, there is interaction, mutual interaction. So I have to see the complete effect of all the charges distributed in the medium. For bundled conductor capacitance, it's exactly similar to what we did for the inductance. For bundled conductor, if you have, for example, one conductor, it will have one radius. If you have, instead of this one conductor, 4 conductors in the bundle, so the radius is changed now. Let's say there is virtual radius for these 4 conductors, which is mathematically will suit your equations. This mathematical radius is simply by, as we did before, we multiply the radius of one conductor with the distances with the other. For example, like here, if I multiply the radius of one of them with the distance from it to the second, from it to the third, and so on to the n, if I have n conductors, root will be 1 over n. The root, maybe I'm getting the 5th root, the 6th root, based on the number of the conductors. We'll see so many examples. We'll see so many examples, different arrangement of the bundles, 3, 4, whatever. And just remember that we have now to replace the radius by geometrical mean radius, by a virtual radius, mathematically, which will suit the calculation. And remember that in the derivation of the inductance, after simplification, we got r dash, which was r, the radius, multiplied by e to the minus 1 over 4. For inductance, it's all r dash, but for capacitance, it's r. This is very important information to keep it in mind when we do the calculation. Actually, the formula sheet will be with you, but remember that whether you are solving from formula sheet or from manufacturer data sheet, for the equations of the inductance, we are using r dash, and for the capacitance is r. Difference is that r dash is equal r multiplied by e to the minus 1 over 4. E to the minus 1 over 4 equal 0.7788. It's only mathematical calculation of the geometrical mean radius, geometrical mean distance. It's the same equation now. If I am finding the capacitance for bundled conductors, Vm, I multiply the distance between the phases. For any geometry of the conductors of the 3 phase, we also will see this in the example. I'll just find the distance between phase A, phase B, phase B, phase C, and phase C, phase A. These, I'll take the 3rd root of them. It's the geometrical mean distance. For the radius, I will multiply the radius of one conductor inside the bundle by the distances from this conductor to all others, and take the 1 over n root of that. This as simple as this. It's very simple. Same equation, the only thing is mathematical representation of the new virtual distances. The distance which will replace this geometrical layout of the conductors. Geometrical layout of the conductors or geometrical layout of the wires inside the bundle. One of them inside the bundle geometrical mean radius, or outside between the conductor geometrical mean distance. Let's take one example. Example is to calculate the pair phase capacitance with horizontal phases spacing of 10 meter using 3 conductor bundling with a spacing between conductor and the bundle 0.3. This same example we solve it for the inductance. This one, if you remember, we solve it for the inductance. Now we'll do that for the capacitance. Equation is simple. Only thing I want to find the equivalent distance now between the phases and the equivalent radius for the conductor in the bundle. We have phase A, B, C. The distances is 10 meter, then I have 20 meter between A and C. So if I multiply all of these together to the third root, I will be getting the equivalent distance. For the bundle, the radius was 1 centimeter, converted to meter, it's 0.01, and I multiply by the distance from the conductor to the other 0.3 by 0.3 to the third square. This is simply the geometrical mean radius of the conductor. D, as we said, we multiply 10 by 10 by 20 to the power of 1 over 3. If I can substitute now in C, the same equation, just I put dm instead of d in that equation, and RBC, which is replacing the R. If you do this, you will get the capacitance in this figure. By the way, capacitance is always very less. The farad, capacitor of 1 farad has a huge area. Normally, capacitance is given in either microfarad or nanofarad or even picofarad. XC, the capacitive reactance, is 1 over omega C. You just multiply omega by the value that you got, you get the XC. Before I move to the next idea, anything not clear in this example? This is the same example that we solved for the inductors. Now we'll have a look at the line conductors. Line conductors, normally we said that we selected aluminum as the conductor for transmission line, being cheaper and lighter. But being lighter, it will be subjected to wind forces and tension strength, which aluminum cannot withstand. So normally, what is dominant, that one, which they call it AAAC, all aluminum alloy conductor, is used in some application, but the most used one is the ACSR, aluminum conductor steel reinforced, where the aluminum strands are in the periphery of the conductor, and in the center there is the steel strands. Normally the ratio between them is like 4:1. 4:1 means the aluminum strands is 4 times as much as the steel strands. We have for these conductors a unit which is used always. You have to be familiar with this unit, which is the circular mill. Circular mill, it's the area of a conductor having a diameter of 1 mil. Mil is 1 over 1,000 from the inch. 1,000th of the inch is the mil. If I bring a wire with a diameter of 1 mil, then it will have an area 1 circular mil. Its actual area is, as you know, pi r square. So you multiply pi by the r, which is d over 2, yani 0.001 over 2, which is 0.0005 square by pi. This is the actual area. But what we are using normally is the circular mill. So circular mill means the area of a wire with diameter of 1 mil. So if the diameter is 2 mil, you will be having 4 circular mills. If you have, for example, let's say a wire of 1 inch diameter, each 1 inch is 1,000 mils. Each mil is 1 over 1,000 from the inch. So each 1 inch is 1,000 mil. If you square this, you will get 1 million. So this wire of 1 inch diameter has an area of 1 million circular mil. 1 million circular mil or 1,000 kilo circular mil. You have to be familiar with this unit. This is the most used unit in a transmission line, and the one is available in tables. Is it clear, the circular mil? Now, as you saw from so many pictures for the conductor, it consists of strands, and they are spaced in similar to this way. This you have only 7 strands, but normally you will have much more. If we take only this example of 7 strands only, and we want to find the geometrical mean radius, we'll be multiplying 49 spacing. So here I multiply the radius of, for example here, radius of conductor 1 with the distance for the others. This is 7. I take the second conductor, multiply it by its self radius by the spacing from the other 7. I will be multiplying 49 spacing and taking the power of 1 over 49 to get the geometrical mean radius, which is not practical. So that's why geometrical mean radius for such conductors is given in the manufacturer data sheet. You'll find it, as you will see, in the manufacturer data sheet. We can do it simply for 3-4 conductors, but for this it's difficult. This is one example from manufacturer data sheet of a transmission line. In this data sheet, you will be given the size, as you can see, in kilo circular mil. First is the name. They are giving these conductors based on their sizes different names. In fact, all of them are like birds' name. And then they will show you the number of strands, aluminium to steel, number of aluminium layers. Anyway, the most important thing for us is GMR. It will be given, and there are 2 values for the inductance and capacitance. We will see these values they modified to make it easier. Now, remember the inductance. We have this formula: 2 times 10 to the minus 7 ln GMD, geometrical mean distance, over GMR. This is the common formula for the inductance. If we multiply it by 2 by F, we'll be getting XL. So I can get XL from this. I multiply by 1609 only to get it per mile. You know the relation between meter and mile. Each mile is 1609 meters. It will be reduced to this. If you multiply this 2 by, I'm keeping F because it's dependent whether you are using, some countries use 50 hertz or 60 hertz. If you do simplification, you will be getting 2.022 times 10 to the minus 3 multiplied by F ln GMD over GMR. This equation, take the constant outside, they split it into 2 parts. First part will be 1 over GMR, the other is 1 GMD. You know from mathematics, this is ln A plus ln B. You can split it in this way. They split it to show that in the manufacturer data sheet, the first part, when you look at it, is GMR. It does depend on the conductor type, while the other one, GMD is the distance. It doesn't depend on the conductor type, regardless of the conductor. It depends on the space between the conductors. That's why it was splitted. The first part is giving XA, the second part is XD. With this, all of this is only simple mathematical simplification. They are given here in the data sheet: inductive ohms per mile and their capacitive mega ohm mile. Only to show that this inductance has 2 parts. One part is dependent on the conductor itself. The other one is dependent on the distance. They don't care about it. So they are giving here for the inductance and the capacitance figure, which is dependent, we'll see now for the capacitance, which is dependent on the conductor type. Other one, it depends on the installation of the transmission line. The same equation we got for the capacitance, split it and you will get this one, two parts. One part dependent on the conductor type and the other part is dependent on the distance. What does this mean? Let's take an example. Dove, when we say dove, one conductor with this name, and I enlarge the information for this conductor. This is the data sheet. There is code, this code paired name for the conductor, and these are the information. I enlarge it, which shows first 0.927 is the diameter of the conductor. And also you can see there GMR. For this conductor, first thing, GMR is 0.0313. Geometrical mean radius from the data sheet, you can see it here. 0.0313. This is GMR, geometrical mean radius. It's shown there up, but when I enlarge it, it moved a little, but it's under GMR. It's always given in feet. These are given in feet. Outside diameter is this figure. You see the outside diameter is 0.927. This is inch. You just convert it to feet. So 0.07725 feet as diameter, radius is 0.03863. This one, this outside diameter is the one, this is 0.927. Just make the conversion between inch and feet, because this information in these tables are in feet. If you get this, you can get XA. XA, the first part, simple, you just 1 over 0.0313. It will be, if you calculate, it will be 0.42. 0.42, you go back to the table, you see it matching, same as in the table, 0.42. For the capacitance, the same thing. Here maybe this example will explain the things. Find the inductive reactance per mile and the capacitive reactance in mega ohm miles of a single phase line operating at 60 Hz. The conductor used is partridge. This is the code of the conductor. Conductor name, which will enable you to get the information from the data sheet. They are spaced 20 feet apart. Now for this partridge conductor, you can see here, this is the table. The GMR is 0.0217 from the table. So you can calculate both XA and XD. When you got this, this will be ohm per mile, both of them, XA and XD. It's only the same equation, the same formula we used before. Now we do this to understand only the data sheet. Why did they do this in the data sheet? To split it into two parts. One of them is dependent on the conductor, the first one, which has GMR. The other one is dependent on the GMD. That sometimes it does make sense, because the manufacturer is trying to give you the information of this conductor. The spacing, it's yours, based on your design, based on your installation, voltage level, whatever. This is the first part, which will be shown in the data sheet. If you sum them together, you will get the total. This is all I'm going to say today. Is there any question? Is the last example clear? Is you have any question? Next time will be, after the exam, will be dedicated a complete lecture for examples. Different example, how to solve them, the formulas that we will need when we use to this formula and this formula, and difference between single phase and three phase, and most important, how to calculate. This will be always in the exams. How to calculate the geometrical mean distance and geometrical mean radius. This one, XA here. XA is something provided in the manufacturer data sheet. It's only one part of the inductance. They did this because if we go back to the equation that we have, simple equation that we have for inductance is 2 times 10 to the minus 7 ln GMD over GMR. Only this, 2 times 10 to the minus 7 ln GMD over GMR. This is the equation that we know that we are using. If we want XL, we multiply by omega L, 2 by F. So it's easy. But for manufacturer, when they do this, they want to provide you with information regarding this conductor. So, okay, the geometrical GMR, geometrical mean radius, which is dependent on the conductor itself and the strands of the conductor. So for this manufacturer, to understand his data sheet, we do only simple thing. We took this L multiplied by omega, we got XL total. We split it into two parts. One of them, we have the common constant factor. One of them will be 1 over GMR, the other one will be GMD. This GMD is the designer. Situation will decide how it's GMD. XA, the first part, which is XA, is dependent on the conductor. So this first part, what we calculated for XA, the part which is dependent on the conductor itself. If we take this example, this is one cable which is being given the code DOV, and these are the information given for, you can see there, GMR is 0.0313. Geometrical mean radius is the information that the manufacturer is able to give you. The other part will calculate it based on your system. This 0.927 is the diameter. Diameter is given in inch, 0.927 inch. You just convert it to feet, 0.07725, then divide by 2 to get the radius. Here, as your question, the frequency is given 60 Hertz. So XA is simply this equation. I substitute by dividing on 0.0313. We said that we multiplied by 1609 because the conversion to per mile, because each mile has 1609 meter, 1609 meter. If you do this, the XA will be 0.42. You go back, check it with the table, you find it the same. The circuit in the right, 0.42. Is it clear now? Okay, I'm done sitting for any question. If anybody doesn't have a question, you can leave. Thank you all. Thank you.